Hello everyone. I'm glad to see you all. It's a pleasure to be talking in front of you about vaccine. Let me introduce myself. My name is Thanachia Sritanyanon, and here's my partner.
Hello, my name is Milin Thanasan Sopon.
I will be talking about vaccine. I have divided my talk into three parts. First, I will give you a background of vaccines. Then I will discuss the mechanism of action of vaccines. Finally, I will tell you about the size of an allergic reaction to vaccines. Why we will always need vaccination? Vaccines have changed the way we think about infectious disease in many parts of the world. Diseases that were once responsible for millions of deaths a year are now considered a thing of the past. Smallpox has been eradicated. Polio is on its way out, and there is a decline in a wide range of other vaccine-preventable diseases like measles, diphtheria, and pertussis. It's therefore easy to get complacent and assume that infectious diseases are no longer a problem. Interesting fact, the first smallpox vaccine was developed by Edward Jenner. What is the background of vaccines? Edward Jenner invented a method to protect against smallpox in 1796. The method involved taking material from a blister of someone infected with cowpox and inoculating it into another person's skin. This was called arm-to-arm inoculation. However, by the late 1940s, scientific knowledge had developed enough so that large-scale vaccine production was possible and disease control effort could begin in earnest. The next routine recombinant vaccines were developed in the 20th centuries. These include vaccines that protect against pertussis, diphtheria, and tetanus. These three vaccines were combined in 1948 and given as the DTP vaccine. What is the mechanism of action of vaccines? Vaccines help develop immunity by imitating an infection. This type of infection, however, almost never causes illness, but it does cause the immune system to produce T lymphocyte antibody. Sometime after getting a vaccine, the imitation infection can cause minor symptoms such as fever. Such minor symptoms were normal and should be expected by the body build immunity.
Once the imitation infection goes away, the body is left with a supply of memory T lymphocytes as well as B lymphocytes that will remember how to fight the disease in the future. However, it typically takes a few weeks for the body to produce T lymphocytes and B lymphocytes after vaccination. Therefore, it is possible that a person infected with a disease just before or just after vaccination could develop symptoms and get a disease because the vaccine has not had enough time to provide protection. Next, how about signs of allergic reactions to vaccines? Vaccine reactions can be classified into two groups. There are minor reactionary and severe reactions. If you have a severe reaction, you must go to the hospital as soon as possible. For the minor reactions, it is more common than severe reaction, usually occur within a few hours of injection, resolve after a short period of time and pose little danger. Local includes pain, swelling, or redness at the site of injection. Systemic includes fever, malaise, muscle pain, headache, or loss of appetite. Includes seizure, thrombocytopenia, hypotonic hyporesponsive episodes, and prolonged crying, which all need to be reported. Most severe vaccine reactions do not lead to long-term problems. Anaphylaxis, while potentially fatal, is treatable without living any long. For the conclusion, well, that's all about our presentation. Today we already presented about the background information of vaccine, mechanism of action of vaccine, and allergic reaction of vaccines. To summarize everything, vaccine prevented disease that can be dangerous or even deadly. Vaccine greatly reduce risk of infection by working with the body's natural defense to safely develop immunity to disease. And why can't we eradicate other diseases as we did with smallpox? This is still the question, and we have some interesting fact. Vaccine prevent more than 2.5 million deaths each year. And we also have a quote from Edward Jenner, who is the first one that produced vaccine. He said that I hope that someday the practice of producing cowpox in the human beings will spread over the world. When that day comes, there will be no smallpox anymore. And before we end our presentation, we also have some short video that make you understand more clearly about how vaccines work. Thank you very much.
Vaccines and the immune response. How vaccines work. Influenza vaccines are able to trigger an immune response by mimicking viral infection. They are usually manufactured using inactivated or killed virus particles taken from various circulating influenza strains. Inactive fractioned viral components contain the subvirion particles hemagglutinin, HA, and neuraminidase, NA. In Canada, influenza vaccines are administered via intramuscular injection. These fractioned particles containing the foreign antigens hemagglutinin and neuraminidase are released from the vaccine into the bloodstream. There, they are met with an immune response mediated by various immune cells, including macrophages, T lymphocytes or T cells, and B lymphocytes or B cells. A major mechanism of action involves macrophage phagocytosis of hemagglutinin, breaking it into smaller components. After ingestion, macrophages display the hemagglutinin antigen on their surface in combination with a specific receptor known as the major histocompatibility complex or MHC. T cells are now able to recognize and bind foreign antigens that are associated with the MHC. Upon binding to the MHC receptor, T cells become activated and proliferate into either cytotoxic T cells, regulatory suppressor T cells, or helper T cells. Activated helper T cells express hemagglutinin receptors specific to the vaccine strand on their surface and play a major role in antibody generation and memory B cell activation. Unlike T cells, B cells are able to ingest hemagglutinin independent of the MHC. Once internalized, B cells process the hemagglutinin antigen and present it on their surface in combination with an MHC. When activated helper T cells interact with activated B cells expressing antigen MHC receptors, they begin secreting lymphokines which have several effects. Lymphokines trigger activated B cell proliferation, which leads to either their differentiation into memory B cells or into plasma cells. Plasma cells produce hemagglutinin antibodies specific to the strain of influenza contained in the vaccine. Memory B cells aid in future immune response when exposed to an active influenza virus. When an infected host sneezes towards an uninfected person, the nasopharynx is exposed to aerosol droplets containing whole, live influenza virus. Once inhaled, the influenza virus attempts viral colonization of nasopharyngeal epithelial cells. Assuming that the vaccine strain matches that of the live virus, hemagglutinin antibodies block viral attachment of live influenza virus to host epithelial cells, and overall disease is either avoided or diminished in severity.